we are ready to perform hypothesis tests using the chi-square distribution. Right? So we have to check our conditions, of course, right? Goodness. All right. Of course, we have to check that it is random, right? So remember, we're gonna remember to say not to check conditions. So, yes, we need to know: does it come from a simple random sample? And then, for some reason, a part of this is checking to see that our sample is larger. Right, so we're going to have to check that as well. Independence, clearly each observation is going to be independent of the other. Usually, that's going to be the case. And then the way that we'll check for normality is we'll look at large counts. And this is where things get a little different. Because in order to check for large count, we're going to have to check that our expected count is larger than 5. All, we're going to triple underline that. All expected counts are larger. 5. So there we go. So those are the conditions that we need to meet. They need to be met in order for us to do the chi-square test for goodness of faith. So we're going to come up with a test statistic, and then we can use our table or our calculator in order to calculate a p-value. For the example that we're going to do right now, we're going to use both. So let's go ahead and get this thing done. So here we go. We are ready to do some inference. Okay, so these can be quite strange. Just because they're very wordy. Very, very wordy. So in this particular example, they did a census in 2000, and they found different percentages of different age groups, right? So they found that 19.1, and this is a census, right? So this is everybody. This is actual, these are, when you're doing a census, you're getting parameters. At least that's the intent of it. You work very hard to get every single person in the population. So we can pretty much consider that these are going to be parameters. So we've got a certain number of people in their 20s, a percentage of people in their 30s, 40s, 50s, and 60s based on the 60 and older, I should say, based on our census. So the question is also worded really weird because it says the table below shows the age distribution for a sample of U.S. residents aged 20 or older, and then it tells you what the sample came from. They randomly dialed landline numbers, and they got a count. we want to know, is this distribution that they got for randomly calling landline numbers, is it the same as the distribution of all U.S. residents, right? And why would you want to do that? You would want to see, hey, are we getting, when we do this random dialing of landline numbers, are we getting a representative population? And you could do a chi-squared goodness of fit test in order to see, hey, is that actually happening? Because if you're going to use that data, you really want it to represent the population. So that would be the purpose of doing something like this. So let's go ahead and perform inference and see, is the distribution of age groups of the people that were randomly called the same as randomly called on landlines, the same as the distribution of U.S. residents? Yay! You get to say a lot of words on the day. Okay, that's good, and that's good. All right. So, H. How about P? So the parameter of interest is the distribution of ages of U.S. residents. All right. So let's get our H on. Let's go ahead and construct our hypothesis. Now we haven't done this yet. So I'll say when we're doing our null and alternative hypotheses for, I said it yesterday, but I'll say it again, for our chi-square test for goodness of fit, it's either going to be that the distributions are the same, or it's going to be for your null hypothesis, it's going to be the distributions are the same, and for your alternative, that they aren't. But you have to state that in context. You can't say the distributions are the same. So our null hypothesis is going to have a ton of words in it, okay? The distribution of all of ages of U.S. residents is the same as the distribution of, I need to make sure that I'm saying it right, of is the same as the distribution of ages of people who answer landline telephone surveys. Lots of words. And that's literally how it's supposed to be. Just a lot of words. It's kind of crazy. Our alternative hypothesis is just going to be that it's not the same. Yeah, got it. So we're just going to pretty much write the same thing, except we're going to put not the same. And we're going to do a lot of writing, and it's going to seem tedious, but we're going to go ahead and do it. All right, the distribution. Weird. All right, hypotheses have been stated. Awesome. They're going to be words. Sorry, guys. But we're dealing with categorical variables. So it's going to be very wordy. Okay. Let's go ahead and check our conditions. With A standing for assumptions. The data comes from a random sample. We need to look and see how many did we get here. A total of, so this table over here represents our sample, right? And the total number in the sample is 1,048. So 1,048 that definitely checks out, right? Because the U.S. population is greater than 10,480, right? So that checks. Okay, so we did the S part, right? Independence, we don't really need to check for. But it goes without saying that I think that one person's response as to what their age is not going to affect another person's response. Yeah. Yes. Okay. All right. Now we are going to go ahead and check for large counts. And I just said earlier, we have to check that all of our expected counts are greater than 5. What does that mean by our expected counts? What are our expected counts? An expected count is going to be what we think. So if we have a sample size of 1,048, and it says that and we have 141 of them turned out to be between 20 and 29. how many would we have actually expected to based on the fact that the entire population has 19.1% of people that are aged in their 20s. So in order to find our expected count, we'll multiply 1,048 by 19.1. So expected count, 1,048 times, and just right. We need the percentage, I'm done. 0.191, which turns out to be 200.2. That's going to check. It's definitely greater than 5. All right, our next expected count, 1,048. How many, so we looked at how many 20-year-olds we would expect to get, right? Now we're going to look at how many 30-year-olds we would expect to get, or 30 people in their 30s, not necessarily exactly 30-year-olds. And that is going to be our sample size times 0.215. So that turns out to be 225.3, and that checks as well. It's bigger than 5. Our next one is going to be people in their 40s. What percentage of people, what is the percentage of people in their 40s in the United States based on the census? 15.5%, so we're going to multiply our sample size times 0.155. Which turns out to be 162.4. That also checked out. I feel like we're missing one. We did 19%, we did 21.5%. 15%, 21.5%, 21.1. I am sorry, I put the wrong one for 40. I'm sorry. I'm not sure how I did that. This should be 21.1. Is that the... Did I underline the wrong thing and everything? Let's see. Oh, I went backwards. It's 21.1 are in their 40s. 15.5 are in their 50s. My bad. So we did this one. We'll keep track. We did this one, and I think this is probably going to be in this calculation 1,048. So this is incorrect. Sorry. It should be 21.1. Actually, I'm going to do this on the calculator now. All right, last expected count. And it's really useful to do this because you're going to use these expected counts later on in your problem. Because remember, in order to get our chi-squared test statistic, you have to have your observed minus expected divided by your expected. Yeah, and you have to square. Yeah, you have to square the difference. Right, square the difference. That's why it's called chi-square. get the difference of your observed minus your expected. We'll kind of look at that a little bit here in a second. All right, last one. No, we got 50s now, right? What are our guys in our 50s? So that was 15.5%. So 0.01 or 0.155. Come on, brain. So 162.44. And then the last one is residents over 60. Our residents over 60. That proportion is 22.8%. So 0.228. So 238.944. Awesome. All of these check out. They are greater than 5. Guys, on the AP exam, if you get a chi-square problem, you are gonna have to do this. Clearly, right? Because our sample size is so large, all of our expected counts are gonna be over 5. But you still have to do this anyways. You can't just say, because the sample size is large, obviously these percentages are going to be over 5. You have to actually do this. All right, so A is done. We're going to actually say all conditions are met. We will continue. With a chi-square goodness of fit test. And pretty much we got in right there, right? T, let's get our test in. Squared is going to be equal to. And we're going to need to get back up to that table. All right, so our observed in this case is 141 for 20 to 29-year-olds. Okay. We just have to put the first couple. Our expected was 200.2 squared divided by our expected, which is 200.2 plus. And we have to put, yeah, we can actually put I prefer to put the last term. The book's not, but I want to do it. So our last one would be, so for 60 plus, our observed count was 286. Be a little less sloppy. 286 minus our expected, which was 238. Point. Interesting. 944. We'll just round that to 94. It's weird. Not a very straight line. And now, We could calculate this whole thing out, or we could go to our handy dandy calculator. And we can do that. We can do this at any time. Going to our calculator. Alright, so we're going to get out our handy dandy calculators and we're going to add a listen spreadsheet page. I'm pretty sure you can't enter count. So you're just going to have to put, you can put US, right, as your expected value. And you can put landline, or just land, or whatever, survey, as your observed. So our expected count, we're going to put in here 200.2 is our first one. Next one, 221.1. An expected count of, nope, my bad, that is incorrect. Next one is 225.3. Next one is 221.1. You guys have these probably written on your paper, so it's probably a little bit easier to enter. I'm having to look back. It's a little weird. And 238.9. Okay. So there are all of our expected. Our observed counts were 141, 186, darn it, 224, 211, 286. Boom. All right. Data is in the spreadsheet. You guys need a moment to finish entering that? Yeah. Areas of conics. Okay. Now I'm going to have to insert a calculator page so that I can let this thing do the test for me. I will hit menu. I was going to say math, but that's not this calculator. Statistics, stat tests, and we're going to use chi-squared GOF. That stands for goodness of freshness. Goodness of fit. Okay, so we're going to hit 7. Our observed list was land. That's what we observed. Our expected list was the actual U.S. population. Our degrees of freedom. So you would think, right? Our degrees of freedom is going to be our number of categories, yes. So it's going to be our categories minus 1. So we had 5 categories, right? We had people in their 20s, people in their 30s, people in their 40s, 50s, and 60 plus. 5 categories minus 1. Degrees of freedom is 4. We hit OK, and we get a ridiculously small p-value. So small. But what I really wanted from that was I wanted to get this chi-square test statistic. That's where we're at right now. I prefer to let the calculator get this statistic. That way, you're really much less likely to make mistakes. Especially if you have 7 different categories. It's going to get, there's just 7 different chances for you to make an error punching in the wrong number on your calculator. 48.229. Pretty good. It's not that different. I mean, that difference in rounding is not enough to throw off the p-value, right? Because if you look at your table, which we'll do here in a second, and interpret this test statistic from our table, we'll see that. So what did I just say? 48.229? I said that? Okay. All right, so, and we're going to have to say, we got a p-value. And in this case, guys, the p-value is so low the p-value is much, much less than that, right? And we need to say with 4 minus 1 degrees of freedom. We need to talk about how many degrees of freedom there is. And since we're on the topic of degrees of freedom, let's go ahead. Did I? Oh, sorry. Thank you. Since we're on the topic of degrees of freedom, all right. So if we did not have the calculator, we will get out our handy-dandy chi-square distribution, and we will look at our degrees of freedom equal to 4. And because the largest value is 20, we could actually have said that our p-value was much less than 0.0005, right? So that's how you would use your table in order to find that, right? So we're looking at this probability, and it is much less than that. Okay. We've obtained a p-value. Let's go ahead and make a decision. So we're saying that, so our null hypothesis is saying that the distributions are the same, right? And this p-value is telling us the probability that they are indeed the same given this particular data that we have, right? So we're going to say they're not the same, right? The probability that they are the same based on the data that we have is very low. So we're going to reject the null hypothesis. Okay? I keep saying reject the. So we're going to reject the null hypothesis, and then we're going to state our answer in context. We would say there is convincing evidence that the distribution of images for is not leasing distribution All right. Excellent. Okay.